All right, so we're talking solutions. Okay, this is a really important part of procedure. There was two important solutions. We decided to add 0.04 moles of H plus that would shoot past the target 0.03 moles of H plus needed to neutralize our 2 tablets of 750 milligram tablets of calcium carbonate. All right, so I want to deliver 0.04 moles. Okay, well, great, I can't count them. So in this lab, we had to figure out what volume do I want to add. I don't want to give you 10 liters in a beaker that only holds 250, so I have to think about the volume that I want to add here. So we said 100 milliliters would be a good value. So we decided arbitrarily, just like we decided 0.04 to be the excess. We know that target is 0.03. We could have made this 0.05, 0.07, but I decided 0.04 would be good. Okay, so we made another decision. As 0.04 moles was the decision of how much excess, we make another decision here is, okay, what is the volume I want to deliver? When someone asks me to make a solution, I always say, well, one of my first jobs was to make solutions in a company, and they said, can you make a 0.4 molar solution? My next question is, how much do you want? Okay, so the volume. So we want 100 milliliters for every table. Because this is the molarity formula, that's 0.100 liter. And now I just solve for exactly the concentration I need to make. And 0.04 divided by 0.1, okay, is 0.40, I'll make it 0.4 molar HCl. I just decided that's the concentration. I need 100 milliliters of this concentration to deliver this amount of moles of H plus to the beaker of the crushed tabs. All right, how do I make that? How do I make that concentration? Okay, well, as we talked about yesterday, we have to, this entire titration, called a back titration, is dependent upon knowing 2 concentrations. We have to know exactly how many moles of H pluses I've added, and we decided 0.4 molar is the concentration I need. And we have to do what? Back titrate the excess. And we decided that if we're going to have 0.01 moles of approximate excess going back, again, it's a target. This color here could be what the lab gives you. Then we said, okay, I want to target 0.01 moles of base, or H plus, so I'm going to need 0.0 moles of hydroxide. 1 hydroxide is going to match up with a H plus. And then we said to ourselves, how much do we want to drop in our burette? We arbitrarily said we want to drop out 20 milliliters. That should be a good target. So we said 0.02 liters. And that created the concentration of the base that we need. It's the molarity formula. 0.01 over 0.02, hey, that's 0.05 molar, and that's the NaOH. This entire lab is based on knowing these concentrations. Now, we talked about yesterday that this concentration was limited because of NaOH being very, very reactive. And so what we do to this? We standardize this concentration, and I'll talk about that, or I did already. We standardize it with KHP, and a lot of guys, like today, the students found this to be not 0.5, 0.8, 0.484 or something. So some people found it to be a lot less. Of course it is. NaOH is reactive. No matter how careful I'm in making it, it reacts with the air, absorbs water, and there's some issues. But I want to talk about making this solution here. How do I make this solution here? All right? So I'm going to get rid of the hydroxide information, okay? And I want to talk about the solution of acid. Because we standardized the base to verify it, well, how do we verify the acid? Well, we don't, because I bought a stock solution. Look at this stock solution. It's 1.0 molar, okay? So this is verified already. And all I got to do is convert this 1.0 molar solution of HCl into 0.04. How do I do that? That's important you understand. Okay, I'm going to show you the steps. And then I'm going to show you an easy formula we're going to use all year long. Okay, in order to figure this out, I need to figure out how much of this do I need to make this concentration of this amount. I want to make, remember, when you ask about making concentrations, how much do you want to make? Well, we want to make 100 milliliters, okay, of this 0.4 molar. That's exactly what I want to make. Okay, so if I know that I want 100 milliliters and I want 0.4, and obviously we came to that, what? Determination, because we wanted exactly that much H plus being added. But if I was doing this without the lag, and I said, okay, I want to make 100 milliliters, which is 0.100 liters, of the 0.4 molar from this, the first thing I would do is say, okay, let's find out how many moles of hydroxide we need. Obviously, when you solve for X, because we already had it up here, you solve for your moles, you're going to get 0.04 moles of H plus. Okay, great. So the first thing I do is figure out how many moles in my solution. Mr. Grazzi, could you make for me 100 milliliters of a 0.4 molar solution? Great. Once I have those pieces of information, I solve for moles. Okay, so I know that the 0.04 moles of H pluses are going to be the same. So I need exactly 0.04 moles of H pluses from this solution. The question is, how much do I need? So molarity is what? Molarity is always moles over liter of solution. I have the moles. I got it by knowing that this is my two target concentrations. This concentration, though, is not 0.4, it's 1.0. And it's verified, standardized. The company backs it. That's why we pay money, good money for it. So what am I solving for here? I'm solving for exactly how many milliliters or liters of this do I need to get this moles. Okay, well, do your algebra. When you get your algebra, you get the liters is equal to 0.04 over 1.0 liters. Clearly that's what? I'm going to get, when I solve for liters, I'm going to get 0.04 liters, which is the same thing as 40 milliliters. So to get the same amount of moles from this, obviously it's what? More concentrated. I need a lot less. That makes sense? So here's what I do. I take the stock solution. I take a measurement device, a very, very precise device. A precise device means that it's going to have a lot of graduations on it. Okay, now you see 50, but what I would do, party people, is I would add, okay, the stock solution and pour it into my graduated cylinder till it exactly hits the 40 milliliter mark. In fact, the meniscus will just touch the 40 milliliter mark. The meniscus, due to surface tension of the water, the adhesion and cohesions, that will hit perfectly at the 40.0 milliliter mark. And if I pour excess or I pour too much or too little, I'll adjust that value with a pipette so it's perfectly on the line. I'm going to spend a good amount of time on eye level to get this exactly at 40 milliliters. I have to make sure I have exactly 40 milliliters of it, because 40 milliliters of the 1.0 molar is exactly 0.04 moles. That's what I'm trying to deliver, so I've got to spend the time. Now, but people make things, okay, once I have 40 milliliters, what do I do with it? Because the 40 milliliters of 1 molar is still 1.0 molar. What am I trying to make? 100 milliliters of it. So what I do with this 40 milliliters is now I add it to a volumetric flask. Now a volumetric flask is a flask that is very, very expensive. And the reason why it's expensive is because it has a high precision. This flask is called a volumetric flask. You can see it's got a little cone shaped, but it's got that little gray line. And what I would do is take my exactly 40 milliliters of my stock solution, and I would pour it into this container. I'd pour it until I'd pour all of it in here. Now this is a 100 milliliter volumetric flask, so I wouldn't fill it all the way. The problem is, party people, I'm gonna have some what? Remnants in here. I can't get it all out, so I'd use some distilled water, wash it out, and add some more here. So I have 40 plus, because I washed it out to clean out the residue. In the volumetric flask, it's not at 100 yet. So what I do is I dilute this to 100 milliliters. So I take my 40 milliliters, right? Which is really represents 0.04 moles, and I dilute to the 100 milliliter mark. I fill this up with what? And boom, cap it, shake it up, and now I have what? A solution that's diluted. Seems like a lot of work there. There's an easier way to think about this. And the best way to think about it is called the dilution formula. Okay, let me show you dilution formula. It is molarity times volume equals molarity times volume. Reason why this works, molarity is moles over liter times liter equals moles over liter times liter. What cancels? Liters. Hey, the moles of my stock solution equals the moles of my target solution. Isn't that what we have here, party people? Same idea. So how do I do this? Very simple. Take your stock solution, which was 1 molar. Check this out, 1 molar. We're going to solve for the volume of this we need. Here's our target. The target that we're looking for is a 0.4 molar solution. And we want to make what? 100 milliliters, or 0.100 liters. Hey, molarity times liters. You multiply. We already did that. So this times this divided by 1, guess what you're going to get? 40 milliliters. We just kind of did it. Remember, this is your target concentration that we're making that's diluted from the more concentrated stock solution. So I just solve for X. And I need 40 milliliters of this to make this solution, but I have to dilute to this volume. That's very important you understand that. And think about it easier. One more thing. What if I'm cutting the concentration in half? What if I'm taking a 1 molar solution and I want to make what? 0.5 molar. Wouldn't I just double the volume? If I want to make 0.5 molar and 100 milliliters of this, wouldn't I need 50? And I dilute it to 100? Doubling the volume, okay, we'll cut this in half. What about question 2 that we just did today? Increasing the volume 10 times lowers the what? Concentration 10 times. So we solve for the stock solution, but then we what? Dilute to this number. Okay, and that's how you make a volumetric solution. All right, have a great day.